If you need to measure the thickness of a single copper wire or a human hair, a standard ruler completely fails. The human eye simply cannot accurately divide a single millimeter into the dozens of fractions required. To solve this, engineers rely on the micrometer screw gauge. The gauge works through mechanical translation. It maps tiny linear distances onto a wide, rotating circle, making microscopic changes easy to track by eye. Look at this diagram of the tool's anatomy. The object being measured sits inside this heavy, U-shaped metal frame, pinned between two flat surfaces, the stationary stud on the left and the movable screw on the right. The reading itself comes from a dual-scale system. You have a stationary main scale carved directly into the central hub and a rotating circular scale attached to the outer cap. The mechanism relies on the screw threads hidden inside. When you turn the cap one full rotation, the screw physically moves forward by the exact distance between two threads. This chart details the foundation of the gauge. We call that exact linear distance the pitch. It is the total distance traveled by the screw divided by the number of full rotations made. By cutting precise threads, you create a system where turning a dial 360 degrees moves the jaw forward by a fraction of a millimeter. But how do we measure an object that is smaller than a single pitch? We mathematically divide that single rotation by calculating the gauge's least count. As shown, we divide the pitch by the total number of marks on the circular scale. If the pitch is 0.5 millimeters with 50 divisions, dividing them gives 0.01 millimeters. That least count is the absolute limit of the tool. It is the smallest physical reality the machine is capable of quantifying. To take a measurement, you simply clamp your specimen between the stud and the screw. Check the main scale for the highest tick mark along the reference line. Here, it's 14. Next, find the aligning circular mark, division 21. Multiply 21 by the 0.01 least count and add it. 14 plus 0.21 gives precisely 14.21 millimeters. Combining the readings from both scales allows the gauge to measure objects down to 1/100th of a millimeter. But physical machines wear down. Over time, as metal rubs against metal, the zero mark on the circular scale might drift, creating a zero error. When jaws close completely, a circular zero hitting the reference line means a perfect tool. If it stops below the line, you have a positive zero error, overestimating size. Conversely, advancing past the line is a negative zero error, underestimating the measurement. Quantifying this exact misalignment is the required first step toward calculating a corrected, reliable measurement. Let's apply this. With a 1 millimeter pitch and 50 divisions, our least count is 0.02. A 6-division lag means a 0.12 millimeter positive zero error. Our raw reading is 3.62 millimeters. Subtracting the 0.12 error reveals the true wire diameter, exactly 3.50 millimeters. The brilliance of the screw gauge lies in this built-in mathematical framework. It uses hard logic to easily overcome its own physical limitations.